Hi, in this video, I'm going to share with you the reason behind why we could simply find the sum of the roots and the product of the roots of a quadratic equation by using the coefficients a, b, and c of the quadratic equation, and that the sum is just negative b over a and the product is c over a. Okay, so why does it work? Okay, so let me explain how we obtain these two formulas. Now, let's consider again that the general form of the quadratic equation to be ax squared plus bx plus c is equal to 0, and that r1 and r2 are the roots of this equation. Now, what I want you to take note is that if we have r1 and r2 as the roots, then it means the quadratic equation also takes the form x minus r1 times x minus r2 is equal to 0. So just to understand that, let me give you a concrete example. Suppose we solve a quadratic equation and it led us to the following roots, 3 and negative 2. Now looking back at a possible solution to this, we should see that x minus 3 times x plus 2 must be equal to 0 before you get the roots x equals 3 and x equals negative 2, right? So in the same way, so even if I state it in a general manner, like r1 and r2 are any values for the roots, then x minus r1 times x minus r2 must be equal to 0. Now, I also want you to keep in mind that r1 and r2 are the roots of ax squared plus bx plus c is equal to 0. So, if x minus r1 and x minus r2 equal to 0 determines r1 and r2, and that ax squared plus bx plus c equal to 0 has the roots r1 and r2, then these two equations must be equivalent. Meaning, we could relate the values or the factors of this equation to that of ax squared plus bx plus c. Okay, so let's continue by simplifying x1 or x minus r1 times x minus r2 equal to 0 so that we could easily relate that to ax squared plus bx plus c is equal to 0. But again, keep in mind that they are equivalent. Okay, so one can be expressed to the other form. At the same time, ax squared plus bx plus c equal to 0 can be expressed as x minus r1 times x minus r2 is equal to 0. Okay, so if I will expand x minus r1 times x minus r2 equal to 0, there are many ways to expand this. It should lead us to x squared minus r2x minus r1x plus r1 times r2 equal to 0. Again, there are many ways that you could expand x minus r1 times x minus r2 is equal to 0. In this case, I particularly use the FOIL method if you're familiar with the FOIL method. And then we could simplify this into x squared, and then I can combine these two. So I have plus r2 or negative r2 x minus r1x plus r1 times r2 is equal to 0. By the way, just in case you're wondering why is it plus r1 times r2, since I used the FOIL method, the r1, the negative r1, so from here, the negative r1 times the negative r2 must be equal to positive r1 times r2. Okay. So, and then we could also have this as x squared and then minus R2 plus R1x plus R1 times R2 is equal to 0. And also, I can arrange R2 and R1, so it becomes R1 plus R2 x plus R1 times R2 equal to 0. If you notice now, R1 plus R2 is the sum of the roots of the quadratic equation, and R1 times R2 is the product of the roots. So we're very close now in relating the coefficients of ax squared plus bx plus c to that of R1 and R2. Okay, so let's get our equation ax squared plus bx plus c to relate that to the one we just obtained. So again, we have ax squared plus bx plus c is equal to 0. So remember what I said earlier, that these two equations are equivalent. Now the problem here is that x squared has a coefficient of 1 while ax squared has a coefficient of a. Now we cannot just assume that a is equal to 1. So we have to make this equation ax squared plus bx plus c equal to 0 be transformed into something with just x squared and not ax squared. But that's not a problem, because all we have to do is to multiply this by 1 over a on both sides. And if we do that, we will have x squared plus b over a x plus c over a is equal to 0. And we can now clearly make a correspondence of each term of these two equivalent equations. Now there is no doubt that x squared and x squared are the same. Okay, so that's the first correspondence. Now the second correspondence is negative r1 plus r2 must be equal to b over a, because they are the coefficients of the x. Since the two equations are equivalent, then we could make that correspondence. And at the same time, the product r1 times r2, the constant from this equation, must be equivalent to the constant of the other equation. So they must be equal. So this is c over a. And if you could see it now, this is now leading us to the formulas that we use in finding the sum and the roots of the quadratic equation. And that's the reason behind. Okay, so we can say that's a proof, or that's the explanation why we can simply use these two formulas. Okay, so I hope you can appreciate the reasons behind getting the formulas of in mathematics, and in this case in finding the sum and the product of the roots of a quadratic equation. They're not just something that you memorize. It is also important if you understand the reason behind, like, how these formulas were obtained. In that way, you get to appreciate the beauty of mathematics. Okay, so let's just take a look at the bigger picture of what we have done here. So I just showed you why the sum of the roots is negative b over a and the product of the roots is c over a. And that is simply by relating ax squared plus bx plus c equal to 0 to that of the equation that came from the roots r1 and r2, which is x minus r1 times x minus r2 is equal to 0. We say that these two equations should be equivalent because they have the same roots, so they must be equivalent. And through some manipulations, we were able to show you the relationship of r1 and r2 to that of a, b, and c. Okay, so I hope you appreciate now the formulas. So after watching this video, you could say, you don't just know the formulas, but you understand how the formulas were obtained. Okay, so that's it.